Hello, everybody. We now come to section 4.9, which is called Newton's method. Now, this is one of the numerical methods available out there using calculus. There are lots of them, actually. Newton's method is probably the most basic and very efficient way to find zeros of a function. Zeros are points where the graph hits the x-axis, where f of x becomes 0. But anyway, Newton found this great and powerful way to find zeros of a certain functions, and that's what we are going to look at now in section 4.9. So there is an area of mathematics called numerical analysis, where people study numerical methods, basically, computing methods, to find certain points on the function. For instance, in this section, we will be looking at these points called zeros of the function fx. These are also known as the x-intercepts, or fx is equal to 0. Sometimes they are called roots, sometimes they are called solutions, sometimes they are called zeros. Regardless of what you call them, in fact, we will just use the word 0 because that seems to be the most common expression. And so we will say a 0 of f of x is any point x such that f of x is equal to 0. Okay, and there are many numerical methods to approximate or to find where f of x is equal to 0. So I should probably give you a little history before we get going on this. Looking at polynomial, if f is a polynomial, okay, we know certain things about zeros of polynomial functions. Okay, now remember, 0 doesn't mean that this number is 0. Okay, 0 of a function is a point, x value, whether it's 0 or not, where f of x is equal to 0. Okay, so x, sometimes this point is called a x-intercept because that's where the function crosses the x-axis. But as far as a polynomial is concerned, the first degree polynomial looks like this, right? And so when this is equal to 0, of course, we know exactly what x is. That's negative b over a, right? So this is the first degree polynomial. Second degree polynomials, these are called quadratic functions. Ax squared plus bx plus c is equal to 0. Do you know how to find the solution to this solutions to this equation? Yes, the answer is the quadratic formula, negative b plus or minus square root of b squared minus 4ac. I'm sure once upon a time you thought this formula is extremely long, and now it probably doesn't look that long. Okay, now if it's cubic or the fourth degree polynomial, there are formulas. Okay, and it's a little complicated. You have to do something before you can apply the formulas. And these are indeed very long and complicated. This goes back to Renaissance time when scholars were facing each other on the duels and to solve these equations. I'm not kidding. This was really what was happening in Italy and areas where the Renaissance was occurring. And there are lots of interesting characters, especially a man named Cardano, who is credited with the formula for the cubic equations, except he stole it from somebody, and they had all kinds of issues. And you should maybe look him up and see what kind of an interesting character he was. But so there's rich history behind the solving equations. Okay, and in fact, the word algebra, the word algebra, comes from the first two Arabic words from the title of a book that has to do with solving equations. All right, but what happens if you have, like, let's say you have, this, I'm just coming up with something crazy, 14 sine of x, 3x minus e to the x plus x to the fourth minus the natural log of x is equal to 0. Can you find a solution to this equation? Can you find the zeros of this function? Now, see, the thing is, you can't, right? Oh, by the way, I almost didn't finish this history lesson here. All right, so what happens is, if the degree is greater than or equal to 5, so people have discovered, and they knew this easy, right? Quadratic The quadratic formula was discovered years and years ago, centuries ago. And as I said, cubic and fourth degree polynomials have nice formulas, ugly formulas. And these were discovered like 300, 400, 500 years ago. And then people struggled during the, I would say, 18th, 19th century because they wanted to be famous for finding a general formula for a fifth degree polynomial, the quintic polynomials. Well, nobody succeeded. Okay, and in fact, the effort all ended when a man, a Norwegian mathematician by the name of Abel, proved that there is no such formula, thus crushing the dreams of everybody else once for all. All right, so this, when the degree is 5 or greater, and this has far-reaching implications in theoretical mathematics, especially in algebra, but Abel proved that when the degree is 5 or greater, then there is no one or general formula for solving polynomial equations. Okay, so these numerical methods actually mean something because sometimes we have to depend on them to find these zeros or approximate these zeros. Okay, and now, of course, this is not a polynomial function, and so this is just hopeless to find any formula. So you have to depend on numerical methods. Okay, and it's not just finding a bunch of numbers closer and closer and seeing if you get some number close to 0. Okay, so here is the most famous and perhaps the easiest of all of these numerical methods of finding zeros, due to Newton, Sir Isaac Newton, and it's called, not surprisingly, Newton's method. So let me draw a picture, and really to understand this concept, what's important is not just memorizing this procedure, which I will give you, but to see why this works. All right, and so for that, you need a good picture, which I'm going to draw now. All right, so let's say f is a differentiable function, and that means it's smooth. And of course, that means as you get closer and closer, if you zoom in and zoom in and zoom into f, eventually, each part looks pretty much like straight line segments, right? So let f of x star be equal to 0. In other words, x star is a 0 of this function. That's what we're trying to find. What is this x star? That's the that's what we're trying to find. So we start with any number you think is close to x star, the real 0 we are looking for. All right, so let me go ahead and write our thought process. Start with any point x naught, and so I am going to draw a let's go ahead and pick x naught to be right here. Oops, I don't have the right pen here. Yeah, okay, so let's say x naught is right here. All right, and so now what do we do with this? We evaluate the function, and we realize f of x naught is not 0, and in fact f of x naught is whatever this thing is, right? So this is f of x naught. Clearly, x naught, my initial guess, is not where f of x is 0. So then we want to get closer to x star, and the way Newton thought about this, very clever, characteristic of Newton. What he thought of is, what? So let's use linear approximation. So we are going to take this, take this line, which is tangent to the graph of f at x naught, and we will find the 0 of that straight line. That's easy to find, right? Because it's a line. And we're going to call this x1. And we will evaluate the function again at this point. Okay, now f of x1 is still not. Okay, f of x1 is still not 0, but it's a lot closer to 0 than f of x naught was. Okay, and so now we're going to repeat the process. All right, so here we'll draw a tangent line, and the tangent line at x1 is going to cross 0, or the x-axis at some point. And so we call this x2, all right? And now we are going to repeat and we evaluate f of x2, that's not 0. And then we will draw a tangent line at x2, and we will find the 0 of that function or the tangent line, and we will call this x3. Now you notice here in this graph, it gets very, very close to x0, right? And in fact, this method, due to Newton, is so simple but so powerful that by the time the third or fourth iteration, you almost get the number that's very, very extremely close to x star. And so this is a very efficient method, surprisingly powerful and fast. And so that's why this method is quite famous, okay? Not just the fact that this is associated with Newton. All right, so start with any x0. All right, so we assume that your random, first guess is not going to give you the real 0. If it is, then you stop and that's it, okay? And then you find the tangent line. Tangent line at x0. So let's call that tangent line, and let's give it a name, L0, line 0, right? L0 at x0, right? And let x1 be, I will say, let x1 be the 0 of that tangent line L1. So in this picture, this is L0, sorry, L0. Okay, so x1 is where L0, the first tangent line, crosses the x-axis. We will call that x1. Okay, now we would suppose that f of x1 is still not 0. In fact, I mean, you are probably never going to find x where f of x is exactly 0. Okay, that's the whole point. We're trying to approximate it. Right now, you also now repeat the process. We find the tangent line. Let's call this, what's a good name? L1, perhaps? Yeah, that's a great name. Okay, at x1. So now this is L1, that's the tangent line at x1. And we are going to let x2 now be the 0. And I say V0 because these are lines, and of course, lines only cross the x-axis at exactly 1 point, right? Unless it's a horizontal line. So the x2 is the 0 of this line 1, right? And then you repeat the process. When do you end? Well, you never do. Okay, so this goes infinitely long. So every problem is going to give you take you infinitely long time, and you'll never even finish one problem. No, of course, that's not gonna happen, right? You'll find that by 3 or 4 processes, by the end of 3 or 4 iterations, your value is going to be so close that they are going to be the same. Okay, in other words, you may find that x3 and x4 are like the same up to like 10 decimal places or something. And at that point, you may as well quit because you found a number that's sufficiently close to the real value. All right, now, if we can somehow program this, and write the expressions in mathematical language, then we can come up with the formula. All right, so let's go ahead and translate this whole process in mathematics. All right, so you start with x0. Okay, so can you find out the equation for the first tangent line, which is the line tangent to the graph of f at x0? Yeah, we should be able to, because here's the point, that's y minus, what is this point? x0, f of x0, right? So y minus the y value at that point, because this point is, this point is on the line, is equal to m, the slope. Well, slope is f prime of x0 times x minus the x coordinate of that point that the graph crosses. So this is again a point, what is it called? The point slope form of the equation of the line. Y minus y1 is equal to m times x minus x1. Right? That's typically how the point slope formula is described. So y is, let's go ahead and figure this out. Actually, what we're looking for is x. Okay, so let's solve this for x. Oh, no. Okay, no. What we want to do is this. We want to let y be equal to 0 at this point. Why is that? Because now we're looking for x1, right? To find x1. So at x1, you want this equation to be right on when y is equal to 0, right? So when y is equal to 0 on L1, then you have found this x to be, x1. So let's say 0 minus f of x naught is equal to, and by the way, eventually you will find exactly the formula for x1. In this case, we're solving for x. Okay, so then what you get is, well, let's see, x minus x naught, that's what we need to sort of isolate, is equal to minus f x naught divided by f prime of x naught, right? All I'm doing is dividing both sides by f prime of x naught. So we find x, okay, which by the way is this thing here because we set y equal to 0. So x, in this case, x1, what we are looking for, that's the next point, it turns out to be x naught minus f of x naught divided by f prime of x naught. Get that? So this is our formula for finding x1 based on x naught. And of course, because we repeat the process based on x1, x2 is going to be all of this, where x naught is replaced with x1. Okay, so let me go ahead and write this. X2 then will be x1 minus the value of the function at x1 divided by the derivative of the function at x1, and so on. All right, so now we can write a what is called the recursive definition. Xn, this will be the nth point, is going to be the previous point, xn minus 1, minus the value of the function at that point, divided by the derivative of the function at that point. Right? This is the recursive formula of Newton's method. Now you can start at any place. Okay, you can start at any place, x naught, and then these will give you the sequence of numbers that gets closer and closer to the real 0. Okay, so that is our method, Newton's method. This is what you will be using for all your problems in this section. And so let's highlight this, make it, bright and attention getting, and so on. All right, now I have what do I have here? I have an example. All right, and so I will sort of, maybe I will just sort of reorient this so that this will make sense when you see this picture later. So that's my second iteration, right? So therefore, right, so this is the first one. We worked hard to get this equation. The second one is straightforward because that just comes from my first one. And then this is the general recursive formula for finding xn, the nth number, the nth approximation based on the n minus first approximation, right? So this is Newton's method. All right, now let's talk about this example. I call this example 1. And so what is that? This function is this. F of x is x cubed minus 3x plus 1. And I need to give you a little warning before I get started on this. All right, so here's my first example. We want to find the zeros of this function. This is a cubic function, polynomial, so you could have at most 3 real zeros, right? And it turns out the graph of this function looks like this, and so you do have 3 zeros. And remember here in Newton's method, you can start at any point, right? You can start at x is equal to 5,000 if you want, but it's going to take a while. So we're going to do something that's reasonable. And let's see, maybe we will start where let x not be 0. Now, if x not is 0, you start here, and you can sort of tell what happens is it's going to give you a tangent line like this, and so x1 will be somewhere here, and x2 will be somewhere here. It gets closer and closer to this point, okay? And that's indeed that is indeed the 0 that we are going to find first. But you can see, depending on where you start, if you start here, then you will probably end up with this 0. If you start here, you'll end up with a point here. So you start with a what I should say is that the 0 you will find eventually using Newton's method will probably be the one that is closest to where you started with, okay? So remember, depending on where you start, you may get different results because the function may have different, more than one zeros. Okay, so let's start at this point, 0, and see what happens with this. Now remember, this is my equation. You have to find the value of the function. That's x, f of x naught, all right? And that's going to be 1. And you have to find the derivative at this point. So maybe it's good to have the derivative here. In fact, I should have done this, and I'm going to do that right now. Anytime you are trying to solve something using Newton's method, let's go ahead and write my computer is going crazy. Yep. All right, let's find the derivative. Okay. All right, let's go ahead and do this. Right. Okay, let's find the derivative. That's 3x squared minus 3, right? So now you say x is 0, so f of x is 1. That's this. And then f prime of x not 0 is -3. And so this fraction, f of 0 divided by f prime of 0 is -1/3. So x1 is 0, which is x naught, minus this number, which is 1/3. Okay, so it started here. Now somewhere it's over here. Okay, 1/3 is, it turns out to be, actually it's going to give you something around here. Okay, anyway, it'll give you a number that's very close. Okay, so this is 1/3. And then next, what are you going to do? F of x1, that's f of 1/3. Now remember, the next thing is to find x2. F of 1/3, and I have done this calculation ahead. It's 1/27. You plug in 1/3 here. 3 times 1/3 is, of course, -1 plus 1. So it's 1/27. The derivative evaluated at 1/3, you plug that in here, is going to give you a -8/3, right? And so x2, once you do this, it's going to be 1/3 minus 1/27 divided, f divided by f prime. Okay, so if you do this calculation, it's going to be a little complicated because you have fractions inside of fractions. It'll be 25/72, and that turns out to be 0.34722. You can probably see the advantage of using decimal numbers as opposed to fractions, because these fractions will get extremely large. All right, so then what do? Find f of x2, okay, and f prime of x2, all right, and then x3 will be x2 minus f of x2 divided by f prime of x2. All right, now by this time, you have a lot of fractions, okay? I mean, a lot of fractions or a lot of decimals. And so, and I hope you see that I'm still following this, right? X3 is equal to x2 minus the value of the function at x2 divided by the derivative at x2. And so on. You can see that it would be very nice to have a calculator or an Excel sheet or something like that. A spreadsheet would be handy, right? Because by the time you get to this point, you'll have pretty messy numbers. And so that's why you can do this, using your app or something like Excel or spreadsheet. And so here is a little screenshot of my attempt to find the first 4 or 5 of these numbers, approximations. You notice here my function is exactly this, right? X cubed minus 3x plus 1. I have also written the derivative here, 3x squared minus 3. And then I enter my, these are the index numbers here. These are the subscript. Okay, so x0 is 0, and x1 is 0.333 as I discovered. All right, and then x2 happens to be this, which is 0.342722. And then I go on and find the value of the function there, the derivative there, function divided by the derivative, and then I subtract this from this number to get this. Okay, so if this number gets really, really small here, this is negative 2.1 times 10 to the negative 9th. So this is like 2 times 1 billionth. That's really, really small. And so you can see these numbers don't change anymore. In fact, x3 and x4 look exactly the same up to 6 decimal places, right? And it turns out the real 0 is exactly going to look like this. Okay, so you can see just by repeating this process 3 or 4 times, you get extremely accurate numbers, right? And that's how you get your solution approximated by this. All right, now I also knew that when I started with 0, I found this number, and which happens to be, what did I say? 0.347296. Okay. What would have happened if I started with 2? Okay, now 2 happens to be somewhere around here, and so when you do 2, this is x0, then xy1 would be somewhere here, and then x2 will be somewhere here, and then this process, if you start at 2, is going to find this 0. Okay, you ready for that? So now let's start again. Let x0 be 2. So now f of 2 is going to be 2 squared minus 3 times 2 plus 1, and that's 8 minus 6 plus 1, that's 3. The derivative, well, I have the derivative written here. Okay, so the derivative at 2 is going to be 2 squared minus 3, and that's 9. All right, and so you can say f2 divided by f prime 2 is 3 divided by 9, that's 1/3. And so x1 is 2 minus 1/3, which is 1.666, and so on, right? X2 is going to be 1.666 repeating minus f evaluated at this point divided by f prime evaluated at this point. Okay, you see the point here? No pun intended. You see the point here? The point is that you just keep repeating this. And also, the other point is it's just going to be quite messy. All right, so once again, I entered these formulas into these cells in the spreadsheet, and I get, I start with 2, and then f of 2 is 3, f prime of 2 is 9. These are the numbers I calculated here. The ratio is 0.333, and x0 minus this is going to give you this, which is that number here. And if you calculate x2, you get this number. x3 will be this number. You see the adjusting factor, or the thing that you subtract from x to the x and minus 1 gets smaller and smaller. By the time you get to the 3rd or the 4th values, these are very close. Okay, so this turns out to be about 1.532. And that is what you found by Newton's method. Okay, so you hardly ever have to go to like step number 5, because by that time the numbers are extremely close to each other. All right, so I knew from the graph that there is one more 0. So what is that one? To find that one, you probably want to start with some negative number. Okay, so finally, and by the way, you don't have to always find all of the zeros, but since I knew from the graph that there are 3 zeros, let's go ahead and find this. Oh, when you enter these numbers, or when you enter this function into your graphing calculator, the graphing calculator could automatically figure out the zeros. Okay, how is the calculator doing this? Okay. Are they using Newton's method? They probably aren't. Okay, because again, from numerical analysis, we know there are many other numerical methods, and some of them much quicker than Newton's method. That will give you an approximate answer very quickly. All right, so let x0 be -2. Okay, then what happens is f of x naught is going to be, you calculate this, that's -2 cubed minus 3 times -2 plus 1. That's -8 plus 6 plus 1. And that's -1. Okay, that's this. And then f prime of x naught is going to be the derivative. So that's 3 times -2 square minus 3. And that's also going to be 9 like before, right? And so the fraction of this divided by that will be -1/9. X1 is going to be -2 minus -1/9. And this will be -1.88888, which is what we found. Okay, repeat this, and you will get this, and x1 minus this is going to give you x2. And again, repeating this, and by this time, the numbers are like in billionth. It's really small, so the numbers don't change very much after third iterations or so, third or fourth iteration. And so the answer is -1.879 or something. 1.879, okay, approximately. So you can find all of these zeros using Newton's method. All right, I'm going to do one more example, and then we will quit and stop the section. This one is kind of fun, I think. Find the square root of 5. Okay, do you know what this is? This is how much I remember. Just again, using a Japanese mnemonic device, which has to do with the bird crying on Mount Fuji, whatever. Anyway, so that is, the very close approximation to the square root of 5. You can't write this exactly because it's an irrational number, non-repeating, non-terminating decimal. So what we can do is you can start with 3, let x not be 3. Oh, by the way, the function that yeah, that's a great question. I have to have a function whose solution is 5, the square root of 5, right? If you're looking for this, of course, you want the square of this to be 5. So x squared minus 5, this will be good because the solution to this is going to be plus or minus radical 5, right? So this is the equation. The derivative is 2x, very simple. So f of x naught is 9 minus 5, which is 4, right? Plug in 3 here, you get that. The derivative at 3 is 6. So x1 is going to be 3 minus this divided by this. Okay, so that's 3 minus 2/3, and that's 7/3. Okay, that's 9/3 minus 2/3, and this is 2.3333. You already see that I started with an approximate number of 3. Now x1 is 2.33, which is much closer to the real 0. And then x2, well, okay, so maybe you can write here f of x1. Now this is going to be a little complicated because you have to square this and subtract 5 from that, and so you can find that, and you can find the derivative at this, and x2 will be what? 2.333 minus f of 2.333 divided by the derivative at 2.333. Okay, and this x2, as you will see, is going to be 2.238. Go ahead and try to do this on your own using your calculator, right, or using your spreadsheet. And if you happen to know how to enter these, small equations or formulas into these cells, and you can iterate this using Excel. That will make your life much easier. I am not going to ask you a lot of questions from this section on Newton's method. It's a rather minor section in chapter 4, but you will have a few questions, and it may be nice if you know how to enter these formulas into Excel. So this is what I found under x2. That's this number. All right. Then you find the value of the function there, the derivative of the at that value, and find the quotient of f divided by the derivative. Subtract this from this number to get that. And again, by the third and fourth iterations, you see the numbers are very, very close to each other, which is also close to this number, which we know to be the real square root of 5. That is Newton's method. And I hope you are impressed with this, thanks to Newton. And again, in the future, you may take classes like numerical analysis and find a lot more different types of methods of finding zeros. Okay, so that concludes section 4.9.